How's it going, everybody? Welcome back to DR Electronics. In today's video, I thought I would cover a recent project I did involving an MQ2 gas sensor. So I actually showed off this board in my previous video going over the very first PCB design that I've ever made. And if you haven't watched that yet, please check it out in the description below. But today I thought I'd cover this project because I initially designed the board and wrote the code for it, got it sent out, put it together, and bootloaded the microcontroller that was on there and tested it to see if it worked, and it had a couple problems. And I figured it would be better off showing the transition of me fixing those problems from both a schematic and layout perspective rather than just doing it off screen and showing you the new board. And I'll also go into further why you shouldn't even make an MQ2 gas sensor board, as nobody on YouTube has mentioned this before, but through a bit of research and asking people on forums, I realized this actually wasn't a good idea to make a project in the first place. But I figured it'd still be a good example to go over as to how to correct your mistakes and learn from them so that you don't make the same mistakes again. So let's jump into the schematic. So in order to see the changes that I need to make, we'll first start off with the block diagram. To give a quick overview of this, there's basically two main sources of power: a 5-volt USB plug and a 3.7 lithium-ion battery. These both tie to an MQ2 gas sensor, although the battery is being boosted by a boost converter, seeing as the gas sensor needs 5 volts in order to be properly powered. We also have our microcontroller of choice, the F030 series, tied to our LDO regulator, as most microcontrollers operate off of a 1.4 to 3.3 volt range. And then we have some LEDs to act as our PPM status indicator, and an LED to see how much battery voltage we have left on our lithium-ion battery. Now, when I was originally designing this, I essentially just tied the boost converter to the gas sensor, the 5-volt output. However, this means that the gas sensor can only be powered off of the lithium-ion battery and not the 5-volt USB power source. So what I added here was a little box saying to tie a power mux into the system. And this is something I'm going to make a video on soon, but basically a power mux can take two sources of input, and depending on the voltage read on the pins that are tied to a voltage divider, if one voltage is higher than the other, it will then use that source as the output. So that's just basically a way of taking two sources and outputting one of them, again, depending on the feedback system. And it's a lot more useful than using a switch, which is what I did here. And I know using these dotted lines and red notes isn't the best way to approach modifying a schematic. However, I don't have Adobe or Nitro PDF in order to make comments, and I figured for something that is just going to be used for hobby's sake and not actually released on the market, this is fine. This can be an exception. But if you actually want to release a product and you want to make comments on either your drawing or someone else's drawing, use something professional and make sure it's neat and easy to read. But that's basically all I needed to add in the block diagram. There really wasn't many changes that I needed to make. Looking at our power section here, it's basic stuff. The notes that I tied the different power labels to were incorrect. So for a while, I didn't know that on schematic pages, you have what are called zones. And these zones are dependent on a letter followed by a number, or actually rather a number followed by a letter. So if we could see here, the original note says 5 volts tied to battery charger, C sheet 3, when it should have said 5 volts tied to sheet 5, zone 3A. This is just a professional way of doing it. A lot of people do this in the industry. You could see this if you look at schematics online. This is just something I didn't know about previously, which is why I wanted to start doing it now. As for this note here, it's just more information on where the zones are tied to. And over here is where the biggest change would be made, where I would put the power mux at the two sources, which in this case would be the 5-volt USB and 5 volts coming from the boost converter, and then that output would be tied to the input of the LDO regulator, which would then output to the microcontroller. So basic stuff in terms of the power section, not too many mistakes here. Originally, when I chose my LDO regulator, the maximum current output that I thought I needed was way overboard, and we'll get into that later, as it was just mainly a misunderstanding with boost converter calculations. But other than that, the power section is pretty solid. There's really not much that needed to be changed, which is good. So thankfully, this part, for the most part, stayed intact. We'll now get on to the microcontroller section. So the microcontroller portion of my schematic was the part that actually needed the most amount of changes. Once again, here we could see the notes need to be tied to their proper zones for the microcontroller, the pogo pin header, UART IC, along with the global label for the MQ2 gas sensor. Over here, we could also see that I'm missing a 100 nanofarad cap in parallel with the switch for the reset line. This I didn't know about initially, but looking at the STM32F030 and F070 application note, we could actually see here a reference schematic that you should definitely follow when trying to make your own custom PCBs. And if we look at the reference schematic here, we could see that our reset switch has a cap in parallel with this. Now, it's not mandatory. I was able to get the microcontroller to bootload without this. However, if you have space to put the recommended parts, you might as well fit them in your PCBs, especially if it's just a one-off hobby project that you're not intending to sell on market. But I'll provide a link for this in the description below, but I had no idea about this when first developing this project, and this is a really good application note for figuring out exactly what you need for your microcontroller in order to actually program it. And even though the datasheet does tell you what each pin ties to, what I didn't realize was these pins here for the UART TX and RX line, if we go to the datasheet for the microcontroller that I selected, on pins 6 and 7 here, it says UART TX and UART RX. So in my mind, I was like, okay, I could tie these pins to that, and then I should be able to use UART communication. But if you see this little 5 here and you click on it, it tells you which device series it's for. And I didn't really know that it was the XC device. I saw the F030 and I thought that my microcontroller was fine, but it actually wasn't. And you could even confirm this if you go to the STM32 IDE and look at the pins that you want to configure. Under your connectivity tab, it'll tell you where the pins are tied to, which is another way I could have verified it. But again, I do find that the data sheets can be a little bit confusing, which is why I was recommending looking into the application notes for the series of microcontrollers, and I'll provide a link for that. But that's basically what I was missing here, along with the boot 0 line. The caps for the crystal, so I wasn't actually able to get this board to bootload with the external crystal. I think part of the reason for that was the caps that I chose. I forgot that capacitors in series act like resistors in parallel, so you don't just add 20 and 20 to get 40. It's 20 times 20 over 20 plus 20, and that's why I have a note here saying to change the cap value to 24 picofarad instead of 20 picofarads, because the crystal that I chose had an overall capacitance of 12 picofarads, the load capacitance that is. So that's why that needed to be changed. And the 0 ohm resistor here, this is dependent again on the crystal that you choose, the frequency of it, along with your load caps, which will vary depending on what you choose. In terms of the other changes that needed to be made, I also flipped the data plus and data minus lines on here, so this would have never actually worked even if I tied the right pins on the microcontroller. So this is why this was boxed in here. And the MQ2 gas sensor itself, I originally just placed it on the board, and I purchased the actual sensor separate from the breakout board on eBay. But what I decided to do instead with this newer version was just use a 1x4 pin header. That way you could use any series of the gas sensors if you wanted to. And I think that would just make it a lot more modular and versatile. Granted, you would have to change some code, but I still think overall it's a better feature to have than to just be stuck with one particular gas sensor. And if you want to change it out, then you have to remove it and solder in a new one. So yeah, that's pretty much it in terms of the microcontroller section. Again, only the major issue I have here is with the TX and RX lines, which, as I explained earlier, there are ways to mitigate this problem. Use the application note, use the STM32Cube IDE, and find the pins that you actually need. So now we'll go to the final section of this, which is the lithium-ion section and boost converter section. So the final section of the schematic here, in regards to the charging IC, the notes need to be changed to tie to their respective zones rather than their sheets. This can be seen for the 5-volt input along with the BAT global label. The resistor here, the 9K, I accidentally ordered a 1206 part instead of an 0603. Once again, this is why I stress to check your footprints and the parts that you're ordering. This is fine for a resistor as it's easy to change, but had this been an IC, it would have been a lot more difficult and I would have potentially had to order an entire new PCB for this. The protection IC here, we could see that the MOSFETs have a drive voltage that's way too high. So what do I mean by this? Well, looking at the part description on DigiKey for the MOSFET I chose, we could see here that the drive voltage is 4.5 volts. That means that this MOSFET will not turn on until there's at least 4.5 volts across the gate. So when I was trying to power the protection IC with my lithium-ion battery, the circuit wouldn't turn on. No matter what I did, how much I charged it, I could not have this PCB be portable. Until I realized, after asking some people online and rereading the datasheet of the MOSFET, that the minimum drive voltage in order to turn that MOSFET on is 4.5 volts. So this circuit would have never worked given the input voltage. I was able to get it to work using my power supply rather than the lithium-ion battery, but that's why I was having issues with this. Also, this 10 milliohm resistor, it's not needed. I thought that it was needed because I was trying to calculate the minimum RDS on that I needed for my FETs based on the maximum discharge current of my lithium-ion battery. Although these calculations are important, I think what I would have been better off doing is just select a MOSFET with a low RDS on. That way the voltage drop isn't too steep, and focus more on the actual load that is being supplied to the PCB rather than the maximum current that the lithium-ion battery can output at a given time. Here also the BAT label that I'm using is used twice. So I have the BAT label here tied to the charging IC to recharge it, and then I have it tied here to read a voltage using an ADC on the microcontroller. This is a massive problem because I have a voltage divider here. So I'm basically taking this voltage and reducing it by half, and then taking that voltage that's reduced by half and tying it to the input of my boost converter. This also caused, obviously, a lot of problems, and it's a big reason why the sensor wasn't reading values properly. I could get it to work using my power supply and increasing the voltage, although again, that wasn't the original intention of this circuit board. So that's why I have this box here saying to change this global label. And once again, it's really important to take a little bit of extra time and make sure that everything in your schematic makes sense. There's no duplicates, your pinouts are proper, you have your different pins tied to exactly where they need to be, and no discrepancies, because if there are discrepancies, you're going to have to fix them. In some cases, it's easy. In other cases, it's not. This was actually kind of difficult because the trace that I tied here was quite large, so I had to cut it with a knife and then make a jumper. Again, stuff like this is going to happen when you first make a PCB, but the less mistakes you can make, the better. And this was really just the massive problem that I had with this board, just the portable section of it not working properly. But overall, this project did work for the most part. I mentioned earlier in the beginning of this video that an MQ2 gas sensor shouldn't even be used in this given application, and that's because a lot of the videos on YouTube that show, a lighter being put near the gas sensor and then an LED turns on and showing the ppm output through Arduino, the gas concentration that's coming from your butane lighter is way higher than what the sensor is actually expected to read. And once again, I didn't know this when making the project, but I figured I'd let you guys know kind of as like a wake-up call that something like this isn't worth fully investing into unless you have the proper equipment and know exactly how much gas concentration you're releasing. Your values won't be too accurate if you do it with the original method that I intended. But with that being said, I'll now show you a quick overview of the updated schematic along with the PCB changes that I made. So real quick, we'll just go over the second version of the schematic. The block diagram section now has its proper block for the power mux. If we look at the power section here, we could see I actually added the power mux in, the TPS2121. Once again, I am going to make a separate video on this as I initially did not know how to use these. But I basically just pulled this from the data sheet and double checked that the resistor values fit with the given parameters that I was working with. In this case, I'm using two 5-volt inputs, one coming from the USB connector and another coming from the boost converter. Here we also have a current limiting resistor to limit the amount of current that could flow at the output of the power mux, and then this global label is just tied to the LDO regulator, which then steps down the voltage and powers the rest of the circuit. And then that is tied into the gas sensor, which is now a 1x4 pin header. And once again, the rest of the circuit with the microcontroller, pogo pin header, UART, etc., etc. Here we could see I added the proper boot switch with the resistor, capacitor in parallel, proper load capacitance, and flipped the UART pins to be tied correctly, along with the UART, TX, and RX pins being moved. If we go to sheet 3 here, we could see that I changed the symbol a bit. I reflected it more so to follow the application schematic. I don't typically like doing it for this particular case because they showed the schematic flowing from right to left as opposed to left to right, which is what I usually do for the most part. But I figured I'd make an exception for this because it was kind of confusing to transfer everything over to make it fit from right to left. So I kind of just left it as is and followed it to the best of my ability. Here we also see that I now have a BAT measure and a BAT global label. So they're actually separate from each other, and the notes are also all fixed as well. If we look at the PCB, we could see that it's quite different than what I originally made in the first video that I showed everyone. So here we could see I actually have a little logo that I made here, YouTube channel name, the month that this board was released. But now I have the power mux section instead of that large switch, the single pole double throw that was taking up a lot of space. The MOSFETs are also much smaller, as once again the amount of current actually needed for this project is only about 150 to 200 milliamps. So I believe these MOSFETs that I chose are rated for 8 to 900, which is more than enough. And other than that, there wasn't really too many other changes. I just made some room for the new boot 0 switch, added a global label here for the pin header, obviously got rid of the respective gas sensor circuitry just for the MQ2 gas sensor, and left everything else the same. So that's pretty much it. There's not much more that needs to be said regarding this project. I figured I'd just show you the changes I made in terms of the layout, part configuration, and just correcting some mistakes that I did to kind of give you an idea of the process that is involved when making PCBs that you're not too familiar with for the first time. But with that being said, thank you all for watching and have a great day.